So last time we moved into this chapter on turbomachinery, we noted that it's devices which either put work into the fluid or extract work out of the flowing fluid. The fluid could be a liquid, and if it's a pump, then that puts work into the fluid. If it's gases, it could be a fan, it could be a blower, it could be a compressor, different names for the device, but basically they put energy into the fluid. That's the goal. For the compressor, it's to boost the pressure. For the fan, it's really to boost the kinetic energy or boost the speed, give it a large kinetic energy. How about work out? Well, they're basically turbines. You could have a hydraulic turbine, like a water turbine, if you had a hydroelectric generating facility to generate electricity with a dam. There's a few of them in the United States, a few of them around the world. Basically, it's liquid all the way through that turbine and extract a lot of energy out of it. You could have a steam turbine or a gas turbine, but those are all extracting energy out of the working fluid. And then the turbines and the pumps and the blowers and the compressors, they don't work in isolation. They work in a system. And so when you put it in the system, often that energy input in a pump or energy input in a blower is to compensate for the losses, the major and the minor losses in the system. So the cavitation data is also on their pump curves. Here is right in this vicinity. It's a little hard to see, but it's net positive suction head in feet. Well, sometimes they put that, but they're reporting what's required. So it's net positive suction head required. That's what they're putting. And it's a little hard to see, but there's the curve for 5, and you just draw it down. There's the curve for 6, and you just draw it down. There's a curve for 7, and you draw it down, and the curve for 8 foot, and the curve for 9 foot, and 10 foot. Sometimes they're just drawn that way. There's other ways they draw them on these curves. So this pump is to operate at 55 GPM. Right here is 55 GPM, and 30 foot of head. So let me come up here. And where is 30 foot? 30 foot is right there. Woo. So 55 and 30 should be right in that vicinity. What size a motor is required? There's two things. The size of the motor, this curve right down here, it says motor horsepower. You need either a half or a 3/4. If you have this size impeller or that size impeller, you need either a half or a 3/4 horsepower motor. What size would you need for this operating point? 3/4. And then the net positive suction head required is round off to the nearest foot. What is the net positive suction head required? Round off to the nearest foot. Is it 5 foot, 6 foot, 7 foot, 7 foot? This is for an inline pump from that manufacturer. Basically, the pipe comes, you just need a boost. You could see that it coming this way because it flows out and then turns and goes into the eye region, gets caught, thrown down and out. There's a lot of pumps out there, different configurations. Here's a big pump. This is a horizontal split case pump, double suction. What you could do is you can open it up, unbolt the top, so you can split it, open it up. There's a big motor here on a skid. The skid to keep everything aligned. That's great if they align it at the factory. If you have a motor hooked up to a pump and you have misalignment, it can eat up bearings so fast. So aligning motors, get it on a skid, you just pallet it in and put it down, hook it up. And the water actually comes in it enters on both sides of the eye, okay, and then is discharged. And you can see the diameter here is quite large, and it's a flanged pipe connection with a lot of bolt holes for bolting it up. Well, this one is operate at 5,000 GPM. All right, that's a lot of flow rate. There's 5,000 GPM. And 275 foot of head. There's 200, there's 300, 225, 250, 275, 275 right there. So it looks like that's the operating point right there. What size motor is needed? Well, this is a line of 300 horsepower. This is a line of 350 horsepower. This is a line of 400 horsepower. You know, you're tempted, but don't put the 400 on it. You need to go larger. And so this is the 450. Now, if you think that that's your design point, but it may actually wobble out and sometimes operate over here or operate over there, well, then you better put on the 500 horse. Little extra safety. Anyway, but I would say it needs a 450 horsepower, brake horsepower minimum. And then what's the net positive suction head required? This curve is a little different. What they did is they put over here the net positive suction heads in either feet or kilopascal, okay? And it's a line that's right here, and it curves up so gently. Let me try and show that again. This line right here, I'm not showing it too well. So what you do is you say, oh, this is my operating point. I'll come up to this point, and then I'll read over, and it looks like I need around 25 feet of net positive suction head. So 25 foot, or whatever that is, in kilopascal, you can get the estimate there. Here's a problem. So we have water, density given, viscosity given, is to be pumped at a flow rate of 5,000 GPM. And there it is in meter cube per second, through a piping network that has 12-inch diameter pipe, or 30.5 centimeter diameter pipe. And the pipe is 700 meters long, or 2,300 feet long, having 6 fully open gate valves. Each gate valve has a K, a loss coefficient of 0.2. So here's an illustration. Here's a pump. Here's a valve, a valve, a valve, a valve, a valve. So there's 6 valves, and each of those valves has a loss coefficient of 0.2 and 10 elbows. So you can just count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elbows. And each of the elbows has a loss coefficient of 0.3. The piping system provides water to 2 heat exchangers, and this one has a loss coefficient of 20, and this has a loss coefficient of 20, because basically once you're in the heat exchanger, it's a complicated flow path. Typically they have a manifold to distribute it and collect the flow in multiple different passages, and you're trying to promote heat transfer, and so you're tumbling the flow over surfaces. You want it to be turbulent, so this has a loss coefficient of 20. This then they give you the roughness of the pipe. This is a very common configuration on, let's say, this campus. We have a chiller somewhere. Okay, well, what's the chiller do? Produces cold water, brings in warm water, and puts out cold water, chilled water. And so there's some heat transfer out of the fluid. Then it's pumped over to a building, let's say this building right here, and we have airflow that goes over another heat exchanger, and that airflow then is cooled, the air is cooled, and so there's heat into the fluid. So Q dot into the fluid, Q dot out of the fluid, and the water goes in a loop. That's what's happening all over this campus. We have an energy plant with a bunch of chillers, refrigerant is isolated over there, and we have a water loop to distribute the chilled water to different buildings. So the question is determine the head loss in the system. So starting from this point, let's say point 1, and going all around the loop back to this point, point 2, that's going to be all of my head losses. When I go from 2 to 1 through the pump, that's a head gain. So what is the head loss of the system? How am I going to calculate the head loss of the system?
We're going to go back to the Bernoulli equation.
Yeah, and so we're going to have the friction factor L over D for the major loss through all that straight run of pipe. We'll have 2 Ks for the heat exchangers, because we're going through two heat exchangers with a loss coefficient. We're going to have 10 elbows, and we'll have 6 valves. And each one of those terms is multiplied by v squared over 2g. Now, if the diameter changes and then the mean velocity or average velocity through these components, or the characterizing velocity that characterizes the head loss, which is sometimes the inlet velocity or the average velocity through the device, if the area of the pipe's changing, the diameter of the pipe is changing, then I have to play with some area ratios. Okay, but everything says that the pipe diameter stays the same throughout the whole system, so I'm not adjusting for that. Does this equation look reasonable? Yeah. Got to get the friction factor. So how do you calculate the friction factor?
Convert the volumetric flow rate.
Yeah, so we basically need to get a Reynolds number over on the side, and then we get the relative roughness, and then we can get the friction factor. But to get the Reynolds number, I'm going to have the velocity. I know the diameter, so I need that speed. I'm going to need it also for this velocity head, the same speed there. And so the speed, volumetric flow rate over area, all that should be pretty straightforward. So for this problem, to calculate for that volumetric flow rate through that diameter, it's around 4.32 meters per second, which gives me a Reynolds number of about 1.5 times 10 to the 6, which with the relative roughness of 0.00082, get a friction factor of about 0.019. A lot of work, but we do have that friction factor. The length we know, that was given 700. So let me start putting these in. 0.019, the length 700, the diameter 0.305. We have 2 times 20. We have 10 times 0.3, 6 times 0.2, and the velocity pressure, 4.32 quantity squared divided by 2 times 9.81. And so when I break that out, I get 43.7 plus 40 plus 3 plus 1.2, all times 0.953 meters. So the velocity pressure is almost 1 meter. Okay. Which, when I sum it up, it is 88 times 0.953 meters. And so when I decompose this or look back, this attributes 50% roughly. This attributes 46% roughly. This attributes roughly 3% and 1%. Does that add up to 100? So it's roughly, it's just 2 significant digits on those percentages. So you see the major head loss is about 50%. The minor losses due to the two heat exchangers, almost 50%, and very little due to the elbows. Yeah, there's some due to the elbows, and very little due to those fully open valves. Fully open valves. These are fully open gate valves. Where did I get this K of 0.2? It's in our textbook. It's in that chapter, in chapter 8. You just have to look back at that table 8. Let me see what page it is on. But it was given to you because sometimes that information is a little hard to find. Like, what exactly is this loss coefficient for a fully open valve? Yeah, 378 on the bottom of the table 8.4. So it says valves, doesn't even show you a picture of them. Fully open gate valve, a K of 0.2. So that's on page 378, table 8-4. Just like the properties, they're out of the appendices, get density and viscosity for water. All right, so the head loss comes in at a whopping 275 feet, or 84 meters. Kind of working in both sets of units. So, what you would want, if you wanted to push that flow rate, if you wanted to push 5,000 GPM through the system as laid out with 12-inch pipe and that many 90s and a couple of valves that can be closed if you need to isolate a piece of equipment and remove it for repair, or, but they're usually normally open, fully open. Well, you're going to need to have a pump that can supply that head, 275 foot of head. So this may give you the maximum flow rate, right? So you're going to design it such that this building over here gets a lot of cooling and it stays air conditioned on the hottest of the hot days over a 10-year period in that city where you have it deployed, right? So you don't want it to stop working on the hottest day of the year. You don't want it to work. But as an engineer, maybe you put in some factor of safety. Somebody says, no, not for 5,000 GPM. Let's upsize it to 6,000. If you said, what's it now going to be at 6,000 GPM, what is going to be the head loss to push 6,000 GPM through the same piping system? Can we estimate that? Can you estimate that? And then can you estimate it for 4,000, 3,000, everything else? Well, we would go back to our basic equation. We'd say our head loss is all of this major loss plus all of these loss coefficients. I'm just going to say all the K's. Okay, the K's from the heat exchangers, K from the valves, K from the elbows. All right. If you had other things like flow meters, something else, and then you had V squared over 2G, true? The dynamic head. Well, what happens when you move from 5,000 to 6,000 GPM? The velocity goes up. How does the velocity go up? Does it go up? The velocity at the new flow rate is the velocity at the old flow rate times the volumetric flow rate, AV of the new flow rate, divided by the volumetric flow rate of the old flow rate. So it basically went up by 6/5. Right? Went up by, what is that, 20%? It was a 20% increase in the velocity. So if it went up 1.2, the new speed is now 1.2 times the old speed. Then what about the new speed squared compared to the old speed squared? 1.44, or 1.2 squared. So what would the head loss do? Well, the friction factor may change, 0.0, 0.019, maybe it goes 0.0191, 0.0912 or something. It's not going to change significantly, right? Especially in your mind, you have a visual image of that Moody diagram. You're starting to get to pretty good flow rates. What does the friction factor curve do for some relative roughness? It goes fairly flat, Reynolds number independent, so that friction factor is not going to change dramatically. At least we wouldn't anticipate it unless it's low flow. But here, look at the Reynolds number, what we had over 1 million. Okay, so the head loss would go up, wouldn't it? So it would go up proportional to the flow rates squared. So this head loss for the second case is the head loss for the first case times the volumetric flow rate over the volumetric flow rate squared. So it would be 1.44 times 275. $396, right at 400 feet. How about if you went to 4,000? You calculate that? You're dropping now this time, right? So it'd be 0.8 quantity squared times 275 be 176. That's like significant drop. True? And then you do the same thing here. What you find is that the head loss drops dramatically as the velocity goes down because it's proportional to v squared, as well as the volumetric flow rate because it's proportional to the volumetric flow rate squared. You're not changing the pipe diameter. So if you wanted to plot the curve for the head loss as a function of the volumetric flow rate for a closed system. What do you mean by closed system? It's not putting it to a higher tank, elevation tank. It's not lifting it, and it's going in a loop. That loop may go to the top of the building, but then it's back down to the bottom of the building. So the elevation change cancels out because you're going up in a pipe somewhere and you're coming down in the pipe somewhere. Okay? Open system is different than a closed system, but this is a closed system. It starts at 0. And what's the shape of the curve? It's quadratic. So the head loss is proportional to or equal to a constant times the volumetric flow rate squared. Go back and don't trust me on that. Check it out yourself. This simple system with some valves and some elbows, 2 heat exchangers and a long pipe, and you'll see, yep, that's what happens. So the system curve has this characteristic, goes 0, 0, very slow rise, but when you start to get the higher flow rates, guess what? It really kicks up, goes a lot faster right in there. So if you want to match that with a pump, remember we talked about a pump. That when you put a pump curve on the same diagram as the system curve, they're going to have an intersection point. And that intersection point is the operating point. And so if you put that pump with that system, it's going to want to flow at this GPM, and the system head loss will be this much, and that'll be the same magnitude as the head gain across the pump, because the head across the pump at the operating point is the head loss by the system at that operating point. So you can now, it's pretty sophisticated. They even have apps on your phone. They have apps on the internet. You can do this on the internet. So I did this on the internet, played with this manufacturer's pump software. And so they'll even say, oh, you specify some things. here is your system curve plotted. They plotted this. I didn't even do it. On our pump curve, and we recommend this model pump for your problem with this size impeller, and they color-coded it red and put it on there. And then they highlight the operating point. Boom, there you go. So at that operating point, it looks like, again, you could read off net positive section head required, as well as probably push it a little bit to the upper right, the size of motor that you'd want. How much of a problem is it if I go ahead and I specify a 600 horsepower motor? It's really not a problem. It's just more initial cost. That's all it is. Okay, that's 600. It's like sending into the weight room somebody that can lift 300 pounds, and you say, go in there and lift 50 pounds. Oh, no problem. They're not even going to break a sweat. That's what's going to be happening with that large motor. It's not going to be a killer for efficiency, etc. It's okay. It's just going to kill your pocketbook when you want to buy it and install it, because a 600 horsepower motor costs a lot more than a 450. The price goes up, 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 up. And then you have to have the footprint for it and the foundation for it, and etc. But if you buy a 350 horsepower motor when you need a 450, you're going to get a call back. You're going to get in trouble as an engineer. People always ask me, why do engineers always specify things? Well, this is why. It's really low. There's really no downside, minimal downside to over-specifying a motor, and yet there's a huge risk if you under-specify one. So what happens now if I put a valve in here and I use that valve not just like an isolation valve, which means it's open always when the system's running, fully open, but then I use it as a control valve, which means I don't want that much flow, and so I'm just going to turn that valve and close it down some. So if you start playing by changing this loss coefficient, maybe it started at 0.2, but you start closing it, it goes to 1, or not point, it goes to 1, or it goes to 2, or it goes to 20. You could start changing that loss coefficient on that valve by partially closing it. What will happen to the system curve? If this was the system curve with it at 0.2, this would be maybe at 1, and maybe this is the loss coefficient at 2. So what's happening? That constant, volumetric flow rate squared, is going up. And the curves will continue to curl up as you add more and more flow resistance. It's pretty easy, isn't it? Isn't this fluid system pretty easy? So that's what would happen. Let's say I had there the same pump running. So the operating point was right here. Where's the new operating point if I partially close the valve? Right here. Did the flow rate drop? Sure did. Let's say I close it some more. Where's the new operating point? Right there. But look at the flow rate did drop again, didn't it? And then it continues to drop and continues to drop. These is the way you used to control the system, because the motor was fixed RPM. And so the motor, you just turned the motor on, it ran happily at 3,600 or 1,800 RPM, and that was it. A little bit of slip, so it wasn't perfect 3,600, it was 35, 20 or something. But they would like to run at that same speed. But this control valve would then close it down because maybe you don't want a lot of cooling. Maybe it's not August, it's middle of June, or maybe it's middle of May, or maybe it's in the spring, so you don't need a lot of flow over to that heat exchanger, so you throttle it down by partially closing a valve. Well, if this is the actual system right here, and then I close it to this point right here, let's just compare. What is the head loss that's across that valve? All of this. All of that is the head loss across the valve. And all of this is the head loss that's across the rest of the system. So using a control valve and using it to really throttle down and change the flow rate, and here all we did was drop it from, let's say this is 5,300 GPM, and I drop it down to 3,500 GPM. It doesn't seem like that huge of a drop, does it? But look, you could see that head loss is high, and almost, what is that, 4/5 of it looks like visually is across the valve. So the energy you're putting in to this pump, 4/5 of that energy is dissipated across the valve. That doesn't seem very wise energy-wise, is it? You see this? And so 1/5 was used of that mechanical energy that the pump put in to push it through the rest of the network. But maybe I'm just using this as an example. You can see this is visually looks like about 4/5. Maybe it's 3/4. Okay, but it's a large percent of that energy is lost just across that control valve. So what do? You try to avoid the use of the control valve by switching to what I mentioned last time. Do you remember? A variable frequency drive or a variable speed drive. They have different acronyms for the same thing, and they're very common now. They're all over. They're in your new air conditioning systems when you buy them to run the fan. You have a VFD for the fan motor on a condensing unit. You have them a lot of places. So as a mechanical engineer, we really should know a little bit about it, so I throw it to you in fluid mechanics. So what happens is this manufacturer even shows you what happens if I take this pump. This pump is supposed to be fed a motor that likes to run a synchronous speed of 1800. With a little bit of slip, that's how induction motors work. It has a 1760 RPM nominal speed to throw out. So this you should hook up a 450 horsepower motor with that nominal speed to run. But if you can take that motor and that shaft to drive that pump and toggle it not from 1760, here's 1760, but to this purple curve right here, and it's hard to see, but that one is 1430. 1430 RPM. What will happen is your performance of that pump will drop. It'll have this new purple curve. Well, that's the way to drop the flow rate from 5,000. It'll drop it down to nearly 4,000 just by slowing down the electric motor that drives the pump. If you toggle it down some more to 1100 RPM, the flow rate will naturally come down to almost 3,000 GPM. And they can really have these VFDs go down to 20% of the speed of the motor. The motor can come down. It probably could come down to 15%. You have a little problem with possibly going like 2% and 5%. What happens is you don't have the airflow that normally the fan is trying to move the air across the motor and cool it internally, and then you could overheat your motor. So you don't want to go too low, but it's made a dramatic difference in the mechanical engineer's world, these variable frequency drives. Now let's talk about open systems. With an open system, typical is that you pump from one tank to another tank. True? And so from this inlet, let's say at 1, through the pump, through some elbows and some pipes, to the discharge at 2, you have an elevation change. Okay? And so from 1 to 2, you have an elevation change. Here's Z1, and there is Z2. So if you say, what is you were going to try to put a pump in there to make the system work, right? Well, the head gain introduced by the pump balances the head loss as well as the elevation change for the flowing fluid. So if we write Bernoulli's equation down, let's just write it one long time. So we have the pressure at 1 divided by rho g plus V1 squared divided by 2g plus Z1 plus the head gain by the pump head gain equal to the pressure at 2 divided by rho g plus V2 squared divided by 2g plus Z2 plus the head losses. Did I write it correctly? Is that okay? Okay, let's say, what about the pressure at 1 and the pressure at 2? Both, it looks like the atmospheric pressure discharging. What about V1, large diameter tank, no negligible kinetic energy at the fall of that surface of the tank. And then we have the head gain due to the pump. So the head gain due to the pump is going to balance the head loss due to the inlet right here. We're going to have a loss, let me change color, a loss, K loss, due to elbows, K elbows, and then the FL over D for the straight runs, the major and minor losses. That's what you're going to have. Okay, that's what we have for the loss. Plus Z2 minus Z1. That's the elevation change. You have to pump it up. Plus, you have the V2 squared divided by 2G. That's kicking it out with the kinetic energy. The pump actually has to throw it out with some non-negligible kinetic energy at the exit. So that's what the pump has to do. And so a lot of times we lump that over. And so what we'll have is we'll have the head loss is equal to the major FL over D plus all 1 plus let's say the K of the entrance plus K of the elbows plus any other K's that you can think of. All of that times V squared divided by 2G. Where did this 1 come from? That may be somebody uses alpha, kinetic energy correction factor. It's the coming out of the pipe, the kinetic energy. And then you have Z2 minus Z1. True? So this term right here gives us a constant times the volumetric flow rate squared. And this is another constant, C1 and C2. So the characteristic head loss part that must balance by the head gain of the pump, it has a different form. It's still quadratic, but it has what we call an offset. So if I wanted to plot the volumetric flow rate as a function of head, the curve would be something like this. Why do we have this not? Why does it go through 0 right there? Because the pump has to lift it before it can really throw it out and move a lot. Right? So the pump has to produce this minimum head due to just lifting it, the elevation change, Z2 minus Z1. All right. So this is a plot of that curve showing you. What happens if I would take the pump right here and I'm trying to draw it out of this tank and I want to pump it into this tank? What's the difference there? I'm trying to take it from 1 and move it to 2. Can you tell what's different? And how would it change my system curve? This is a system curve. It'll actually start below zero. Basically, you're going to have it closed, otherwise it's going to flow. You're going to have to valve close it, or otherwise it'll flow. And the other thing is, let's say this pump does nothing to it. It'll actually come across, and that'll be the nominal drainage, kind of siphoning type of flow rate. And then if you turn the pump on, now you can even get a higher flow rate. So, there you go. Well, we could put pumps in series. What does that look like? Here's one pump, followed by another pump, followed by another pump. Or we could put pumps in parallel. And pumps in parallel are very common. Why? Because they allow us to have redundancy. And so maybe I have a system for pumps in parallel where maybe on one day I need to just run pump number 1, and the other day I need to run pump number 1 and number 2, and on a really hot day I need a lot of water going all over campus. I need to run pump number 1, number 2, and number 3. But on a modest day, I shut off pump number 3, or I start playing with which pumps to shut off and turn on. Now, it's easy to analyze the pumps in series as well as pumps in parallel if they're the same pumps. That's nice. Sometimes they're not the same pumps, but let's just consider the easy case, they're the same pumps. So each pump has a characteristic curve that looks like, let's say, this. True? This is the pump characteristic curve. What happens if I put 3 of them in series? Let me just try and draw it on the same. What does the composite look like if I put 3 of those same pumps in series? Well, do I get a higher net flow rate through the system? Or what is this point called for that one pump? It's the free delivery. So I'm not going to get the higher free delivery through the whole 3 systems. But what I'm going to get is I'm going to get a head gain, and then a head gain, and then a head gain for whatever operating point it's at. So basically you take that one pump, then you add to it another pump, then you add to it another pump, and so the composite curve would be way up here, and then it would fall off, come down. Maybe I didn't do the shoulder correct. Maybe the shoulder needs to be tucked in a little bit more, but I think you get the point, is that the head is 3 times higher. Where it's the shutoff head is 3 times higher. So if I actually close the valve right here, I'd have the shutoff head for the first pump, second pump, and the third pump trying to open that valve and push through that valve. All right. Well, what about these 3 pumps in parallel? Well, it's just the opposite. Let's try and come down here and put our 1 pump in. And now you could get the flow rate through 1 plus the flow rate through 2 plus the flow rate through 3. And so it'd be like, but they're not going to increase the head, are they? And so the composite curve would be something like this. So you could get 3 times the flow rate, but the head would be the same. And once you have 3 pumps that are all the same, then you make 1 pump big, 1 pump small, and then do it again. And it's a little more challenging, but I think you could figure that out. Here's a clicker question. So, head is summative when 2 pumps are connected in. Hey, don't call these things out. I heard the answer. Head is summative when 2 pumps are connected in, either series or parallel. Yes? All right, let's go see where we're at. Are we 100%? Man, you're good. All right, so what's the next clicker question? Flow rate or capacity is summative when two pumps are connected in. I mean, is there any even, hey, there is one person. What are we doing? Polling has stopped too. All right, we're locked in on that one. Well, the flow rate is when they're connected in parallel. Well, we talked a lot about centrifugal pumps. There's some positive displacement pumps. They have almost completely different characteristics or behavior. But the positive displacement pumps are very, very prevalent. Maybe not in a commercial setting like moving water through buildings, but in a medical facility, in the hospital, you go in and you see what they're doing to drive the IV and the pumps hanging, dangling. Go visit your grandmother or somebody in the hospital, right? Some friend or somebody. And you'll see all the equipment, and all that's heavily engineered, very engineered. Peristaltic pumps, so they'll have a tube, and it's a flexible tube, and they'll have a device that's rotating, and it's squeezing and pushing a trapped amount, and it can deliver, guarantee, that flow rate. So the nurse can come in there and look at the doctor's orders and then verify or move that knob to give you the right flow rate for whatever IV you're getting. So this one's very common in labs, in chemistry labs, physics labs, just when you have to deliver a specified amount over a long time period, very controlled. Another one is a rotary pump. Now, where do you see some of these? How many people have ever taken apart an engine that drives your car, in your car or engine? Anybody? How's the oil pump work in a car? Right there. It's a rotary pump, just like this. Okay, some of them may be more like a gear pump, but a lot of them are like this, rotary pump. Okay? Really? Nobody's taken apart a car engine? This many people? The water pumps are more centrifugal, okay? But an oil pump, it wants that engine to get that oil, and a little bit of resistance to the delivery of oil, and a positive displacement pump says, I'm going to give it to you. You need the oil, here it comes. And so that's why they have those type of pumps. It's going to have a flow rate linked up to the RPM, yes, but it's going to be very controlled. Here's a gear pump, and then here's another one where you have a double screw. So they're always trapping and then pushing through a particular volume. Now, what about the performance of these positive displacement pumps? Well, they're designed to deliver that flow rate. And they're going to deliver it almost, it doesn't matter what type of resistance they get. They're going to break trying to deliver that flow rate. So the range of the flow rate's very narrow, and if there's some resistance, the head that the pump produce will go way up. And then typically something will happen where it'll break. Something will break. Okay? If you can have these pumps, and if you do something wrong, something will break somewhere in the system. The pump will break, or a line will break, a hose will break. But they have a wide range of operating pressures or head, but then if you try to go above, it's not designed to operate up there, and you don't want to operate a positive displacement pump up in that region, typically. No applications that I know of. So this would be changing the viscosity of the fluid. Maybe it's cold oil, maybe it's hot oil. It doesn't matter, it's going to go. Okay? Same with the water and IVs. You're just going to get that fixed delivery. Now we talk about pump affinity laws. Affinity. Well, what's affinity? You can look it up. Just say define affinity and then read it. So, a similarity of characteristics suggesting a relationship especially a resemblance in structure between, well, animals, plants, and languages. But we're looking at an affinity relationship for pumps, equipment. So they look, they have the same structure, the same characteristics. So when you take a look at a pump, you can say, let's think about, if I'm interested in predicting the brake horsepower, well, that's going to depend on the rotational speed of the shaft. It's also going to depend on the volumetric flow rate, the density of the fluid, the viscosity of the fluid, the diameter of the impellers, and some surface roughness with the material that's made up of the impeller in the volute region, in the casing. And so you think, okay, well, this is the head generated by the pump. It's a function of all of these parameters, and you do a dimensional analysis. You can do the same thing for brake horsepower, dimensional analysis on that. But what you find is you get so many pi groups. Here's one of the pi groups that the textbook discussion, which is out there in vast majority of literature in fluid mechanics. Another pi group, another pi group, and another pi group. Well, this pi group you recognize already, right? Roughness, so that's relative roughness. These other pi groups, I'm sure if you were the first person doing it, maybe you would play around which is the best illuminating group. But what is this group linked to, pi 2? It's linked to the flow rate, right? What is the next group, pi 1, linked to? The head gain. So it's like flow rate and head gain. What is this third pi group linked to? Well, that's a little harder to see, but you see the rho over mu, and you see a diameter. Oh, wow. If I just had a V right there, that would be it. Wouldn't it be a Reynolds number? A ratio of inertial to viscous? But this other pi group, they don't have they put a omega D, which has the same as a V. Same properties as length. So this is like a Reynolds number. So this is like dimensionless head gain, dimensionless flow rate, dimensionless, well, inertial to viscous, a Reynolds number, and relative roughness. Then they talk about the head coefficient, giving it name. What was this one? Wasn't that our pi 1? Well, you can give these pi groups names like Reynolds number, friction factor, relative roughness, head coefficient, capacity coefficient, even power coefficient. They didn't show it here, but it's in the discussion in the textbook. And then what you have is you can put dimensionless flow rate instead of instead of physical flow rate with units. So this is the Q sub C, the capacity coefficient. What about this scale? The head coefficient. And so you could plot the head coefficient for that pump as a function of the capacity coefficient. You could then do the power, C sub P coefficient as a function of the capacity coefficient. And efficiency, you could look and say, hey, they have the same shape. So you develop the affinity laws. Sometimes people don't use that. It's pump affinity equations. It's not like a law like, stop or speed limit's 55. In science, they use laws for everything. It's this law and that law. And then they said, look, everything's not a law. Some is just a relationship. So the affinity relationships. So they say pump A and pump B, they are scaled, different diameters, different flow rates, different speeds, and then they can get the relationship such that the volumetric flow rate through pump A and B are related by the ratio of the speeds, the ratio of the diameters cubed. All right. So that falls out of the dimensional analysis. Same for the head and the brake horsepower. How would we use something like this? Well, in a lot of cases, you don't change. So for the simple case, the diameter of A is equal to the diameter of B. It's the same pump. But what are we going to do to the pump? We want to increase the flow rate, so we speed the pump up. Remember we had that variable frequency drive? You know, those variable frequency drives can go from 100% to a little bit more. They can actually make it go faster. So maybe they can go that 105 or 110, 110% of the nominal speed. Okay, so they could change the speed. That's very, very common, and of the same pump. Well, what does the changing the speed do to the flow rate? So think about this. The volumetric flow rate for the new case is equal to the volumetric flow rate of the original case times the new speed divided by the original speed. So if the speed went up by 10%, the volumetric flow rate went up by 10%. If it went down by 70, or whatever it went down, the same ratio. Let's take a look at the next relationship. What about the head gain? So the new head produced by the change speed of the pump is equal to the head, or the original head, times the new speed divided by the old speed squared. So if I went up 10%, then the head would go up 121. It would be 1.1 squared, which is 1.21. So it didn't just go up 10%, it would go up 21%. True? That's what the head would do. How about the last one, the brake horsepower? So I'm supplying that brake horsepower for the new case, and let me just move this down so you can see it, is equal to the brake horsepower for the original case, and the density of the fluid I'm not changing, the diameter of the motor I'm not changing, just the speed I'm changing. Well, it's the new speed over the old speed cubed. So let's stay with our 10%. What's 1.1 cubed? So it went up 33%. So if, there's a great application, if the speed omega B is equal to 1.1 times omega A, then the H, let me use cap H because they use cap H, of B is equal to 1.21 times H of B, and the brake horsepower of the new case, 1.33 times brake horsepower of A. There's lots of applications of this. Maybe not so much in pumps, but definitely in fans and other things. But it's the same type of turbo machinery, fan and pump. I know we spend a lot of time talking about pumps, but the same applies. So typical, you have a motor, and the motor comes out and there's a pulley. And the pulley goes to a belt that drives another pulley, and that pulley is connected to a shaft, and you have a great big squirrel cage blower to air handler, to move air. And so the air is ingested into this, into the eye region, and then it's blown out that way. And then the new engineer, the young engineer, new job, and he undersizes that blower. He undersizes the fan. And he needs to increase the volumetric flow rate right there. And he says, ha-ha, I learned in fluid mechanics that if I make it spin faster, then I can get more flow out. So he tells the mechanical contractor, change the diameter of one of these pulleys, and I'm going to tell you what to switch it out. You know, change it from a 20-inch or 10-inch to an 8-inch or some other. And the same electric motor is going to be driving it, but now the pulleys are going to make it go faster. And you'll have to adjust the belt a little bit, but you can handle it. And then that's great, and now he's boosted the volumetric flow rate. The new volumetric flow rate's 10% greater than the old volumetric flow rate. Everything's running okay for a day or two, or a week, or a month. And then what happens is this thing gets toasty hot and burns out. What didn't he consider? is the brake horsepower to make it go only 10% faster? Isn't 10% more? And maybe that was a perfectly sized 5 or a 50 horsepower motor, but now you are asking it to do a lot more than a 5 horsepower motor can do by just changing the pulley. And it runs a little bit because the motors will take an overload. They'll take it for short time periods, but they won't live like, it's just like, you ever been in a job environment where you kind of feel like you're always abused as an employee?
Yes.
Yeah. Go do it, go do it, go do it. You'll do it, and you'll do it a couple times, but then it gets old, and it's like, you know what? I'm not going to be giving it 110% every day and then told the next day, step it up and give me another 110%, So usually you go look for another job or something. You're abusive relationship there. Well, anyway, that motor is going to do it for a while, and it's going to try real hard, and it's just going to burn out. A pump delivers 10 meters of head at 44 liters per minute at a rotational speed of 1200 RPM. If the pump efficiency is 83%, predict the brake horsepower. So how do you calculate the brake horsepower? Well, it'll be 1 over the efficiency of the pump times the fluid power. The fluid power is the head gain times rho g of the fluid times the volumetric flow rate of the fluid. True or false? Is that equation good? See how much you've learned already this semester? This is incredible. And the people that sent you to college said you couldn't learn. Oh, that's not true. Come on now. 10 meters. What are we pumping? Water? I need to know the density of it. So let's say it's water, 9.81 kilonewton per meter cubed. And a volumetric flow rate, liters per minute, so 44 times 10 to the minus 3 meters cubed per 60 seconds, and divide by 0.83. And what do we pick up for the answer? Brake horsepower. $86.7 watts. Does that look okay? So the brake horsepower. If the rotational speed is decreased by 10%, so the speed, let me try it over here, omega of the original case is 1200 RPM. And the omega of the new case is decreased by 10%, so isn't it 90% of omega B, or omega A, the rotational speed of A? True? So what is the new rotational speed? So the new rotational speed is true or false? Okay. What is the new volumetric flow rate? Well, the volumetric flow rate of the new case is equal to the volumetric flow rate of the old case, and the relationship is they're linearly proportional to the rotational speed, so omega of B divided by omega A. So this is the volumetric flow rate of the original case times 0.9. So the volumetric flow rate was 44 liters per minute, and it's the volumetric flow rate of the new case 39.6 liters per minute. True? What about the pump head? So the head of the new case is equal to the head of the original. Whoops. And then it's the rotational speed squared. I'm using the pump affinity laws or equations or relationships. And so it's 0.9 quantity squared. It's 81% of the head. So the head 0.8, whoops, 8.1 meters. And then the brake horsepower. Brake horsepower was 86.7, but it's the rotational speed cubed. So 0.9 cubed is 73% of the 86.7. So the brake horsepower goes down to 63.2 watts. There's some ways to think about, to recall these relationships. The diameters, you're just going to have to look up the equations. But when it rotates, think about in the eye region, it's like slicing into the fluid and cutting it into the fluid, and it's grabbing so much fluid. And so the volumetric flow rate is proportional to the rotational speed. Okay. What about the head? Well, you're slinging it out. It's kinetic energy coming off the tips of those impellers. Isn't it rotational speed? Then you have the omega squared. So the head is proportional to omega squared. Okay? It's the kinetic energy which is related to the rotational speed and the outer diameter. So that velocity squared gives you omega squared. That's proportionality. And then for the brake horsepower, well, that's going to be proportional to the head gain and the volumetric flow rate. So you already pick up omega squared from one and omega from the other, and so the brake horsepower is proportional to omega cubed. So the speed really changes dramatically as a function of omega, the speed cubed. Well, we finished this chapter. I did it. Okay, I wanted to do it. So we talked about pumps especially, but the same equations apply to fans and blowers and compressors, where these are all applied to gases and pumps of liquids. Turbines, we have turbines for liquids, turbines for gases, turbines for steam. You have major components of the pump. Just think of liquid pump, eye, impeller volute region, or casing. Talk about the pump curves, free delivery, shut off, efficiency, brake, best efficiency point, brake horsepower, and then net positive suction head required for a pump. For a system curve, make sure you know the difference between an open and a closed system. Sometimes I've seen some young engineers specify stuff. It's like, what were you thinking? Well, it has to push it all the way to the top of that building. But it's a closed system. It's going to fall on the other pipe coming down. There's no delta Z because of the distance from the basement to the top of the building in a closed system. But if you have, let's say, an energy plant, you have a pump in the bottom and it's taking water and then it's spraying it at the top, well, now you have a delta Z difference. It's an open system. It's broken. At one point it's open to atmosphere, at a different elevation it's open to atmosphere. So make sure there's a difference between open and closed system. And then you have this head loss. So sometimes for an open system you have to pump it uphill plus overcome the head loss. For a closed system it's just the head losses. What are the head losses? They're the major and minor head losses. Operating point is when the pump and the system have the same head and the same flow rate. So they match. So what goes through the pump as a flow rate will be what goes through the system, and then what the head gain across the pump, the only input or gain in the system, is lost throughout the rest of the system. Okay, that's how you get our operating point. You could control by adding head loss. That's kind of old. You want to avoid. But a lot of systems still. Actually, what they do, you wouldn't believe it, they would have a brand new system, and then they would have a couple valves they knew they're going to go out there and they're going to adjust to get it to the operating point. So it would be going a little bit faster than it needs to. Then they adjust that valve and walk away for the rest of the life of the building. And so what's happening is you have some energy put into the building, into the pump, the rod and the fluid, and it's perpetually being wasted through a partially closed valve to balance it. Lots of places. So as a young engineer, you may be tasked with energy efficiency. You may want to go looking for some of these things. Equipment that's not running right. Or things that's like, hey, why is this valve partially closed? It's always been that way. Well, let's strip it out, open it up, and put a VFD somewhere in the system and toggle down the speed. That's what you do. So variable speed drive, variable frequency drive, what the magic is, and I wish I had more time to talk about these things because I think they're so innovative and so profound. I mean, they're about 15, 20 years old now, but they're out there and they're being placed all over, is that you change the frequency. Is that the right symbol for the frequency of the electric current? What is the symbol for the frequency? Oh, frequency. Frequency of the electric current and the voltage, the EMF of the electric current that's fed to the motor. You just can't leave it at 110 volt and just toggle it down in frequency. It'll burn out the motor. You've got to bring down the voltage as well as the frequency in the right proportion, and then the motor's happy. The electric motor's happy. And it took some advances in power electronics, not your cell phone electronics. Power electronics can handle those amperages and voltage and high-speed changes to make that work. And so you can buy them. They're very affordable. How to put pumps and analyze them in series and in parallel. Talk about positive displacement pumps. We just wrapped that up, as well as the affinity laws and how to apply it. Let me go ahead and shut this down, and I'll have a few minutes for questions. Okay?